I also wanted to do a real quick review of Kepler's three laws using this animation that that I found online, and there's a link to it in the Blackboard notes that are posted. Just real quick again, notice that this white circle around here, the white circle that you can see, is represents Earth's orbit, and you can see when we show the empty focus and the center that basically, although it's not quite a circle, it's very close to a circle. So if we show an animation of the planets in orbit, the white one is Earth, or where we're having a animation rate of a 5-second year. All right, so it takes 5 seconds to go all the way around. There's no real noticeable place where it gets closer to the sun or any real noticeable difference in the speed. So that's Kepler's first law, says that they're actually ellipses. So if we exaggerate this ellipse and we show the empty focus being farther and farther away from the center and the other focus where the sun still is, you can see that the white dot swings around much more quickly when it is approaching the sun, and the elliptical orbit, which is actually a demonstration of Newton's second law, faster near, slower when it's farther away. And we'll learn in AP Physics, like I said, next year, that that is a manifestation of conservation of angular momentum due to zero torque resulting from the gravitational pull. Kepler's second law also shows us that we can plot out in equal times that the planet will sweep out equal areas. So each one of those represents roughly a month. There are 12 divisions, each with the same area, but vastly different shapes. Because over here on the left, where it's very close, it's moving much more quickly with short, fat wedges, and over on the other side to the right, near the empty focus, it's moving much more slower with longer, thinner wedges. Okay, we can erase the sweeps and just show anytime I push this button now, it'll sweep out a month's worth of area, so that area is equal to that area, and then of course we could do it continuously, like I said, and then it would just show each one as one of 12 months. Kepler's third law here, it just demonstrates some of the math and the graphing. Here, if we do a logarithmic graph, or we do a graph of all the axes squared and cubed and everything, we could get a line with a slope on it, with a slope that would be equal to gm over 4 pi squared, and from that we'd be able to determine the mass of the sun if we didn't already know it. Then here are the Newtonian features. We can just add vectors and lines of action for the for Earth as it goes around. You can see that the gravitational force vector, the red one, gets smaller when Earth is farther away. Here, let me erase the sweep so you can actually see that. See that red vector right there gets very large when it's near the sun, because gravity is an inverse square law. So when it's half the distance, it's 4 times the size. So here, where we're over near, we're at like maybe 1/5 or 1/6 the distance as we are when we're all the way on the right. It will have like 25 to 36 times the length, right? The squares of 5 and 6. And then the line of action is that velocity vector. Notice the blue one is always going to be tangent to the path that the Earth is taken. Okay? And one other thing I did want to show you, if we go back to Earth-sized orbits or Earth-shaped orbits, get rid of this other stuff, is that you can see that Earth is not only traveling in a larger circle, or larger ellipse, excuse me, of a larger radius, but it actually is moving slower. So it takes longer for a year, not only because it's going a farther distance around the circle, but it's actually moving slower within the circle. We can step back out to the orbit of something like Saturn or Uranus, and we slide way out here. You can see that the white one is Uranus, I think. Yep, and so you can see how slow that's moving compared to the others. And if we speed it up a little bit, we can see that the inner ones are literally flying around much greater speeds. Okay, so those are the harmonics, or the relationship, the resonance between the period and the orbital radius.